Down with the glasses, Lars and Christian. All of them work for a spin-off of the Ruhr University Bochum. Please welcome them with a huge round of applause.
Yeah, so thank you very much. Thank you for being here. I'm Christian. The tall one is Lars. The muscle man is David. So yeah, we are coming from Bochum. It's a nice city. It's like 2.5 hours away from Leipzig. It's very close, more or less. Yeah? FISEC is a spin-off of the university. We are now like 2.5 years old. And this is actually the very first time that we really present insights of our technology. Yeah? So the research team behind the Enclosure PUF technology is not just we three. The major people are also Christoph Paar. He's professor for the chair of embedded security at Ruhr University Bochum, as well as Johannes Tobisch. He's also here, but he's super shy, yeah, so he don't want to be on stage. That's a joke. Yeah, 3 people are enough. Yeah. And ourselves. Yeah. So you maybe, of course, know Bochum because of the Ruhr University, specifically because of the Horst Goertz Institute for IT Security. But you maybe also know Bochum because of Nokia and Opel. But because we don't have Nokia and Opel anymore, we also created the FISEC to get all the people. This is not true. Yeah? It's actually true that we have 26 professors at the HGI. We have more than 100 alumni, and we are one of 15 startups, where some of them are already no startups anymore. And this is a nice ecosystem for us and for IT security. Yeah. In Bochum, there will also be the Max Planck Institute for Cybersecurity and Digital Privacy, which is pretty nice. We have the European Competence Center for IT Security. We have the Flux Fingers, yeah, they're also here. And I guess Bochum is good in publishing real-world attacks. And real-world attacks are also our background, specifically the real-world attacks on embedded systems. Yeah? And to get an idea what we are actually doing when we are not presenting like novel technologies like this, as I said, implementation attacks. For the people who like statistics, physical unsecure IoT devices are actually the major concern for the IoT, so for the Internet of Things, for all the connected devices we will have in the near future, which is a real issue. However, who likes concrete examples? Of course, we have a lot of different attacks, like mathematical attacks, social engineering, but specifically implementation attacks. And implementation attacks can, again, be classified in different families, yeah, like the active and passive ones. The passive ones for like side channel attacks, where you use just the timing of the algorithms, electromagnetic emanations or power consumptions, and then maybe some simple analysis or even maybe some statistical analysis, you can easily extract the keys. I will show you some very rough examples later. Yeah? And on the other side, we have active attacks. Again, the attacker has the device and can maybe inject faults, maybe with lasers, maybe with clock glitches, power glitches, or reverse engineer the entire device. Yeah? And what is important, these attacks are independent of the algorithms or of the math. Yeah? You can apply them to virtually all ciphers in the field. Little illustration of power or timing analysis using maybe picoscope or an oscilloscope, or injection faults in the chip. Concrete examples are given here. The credit comes or goes to our chair, to the chair of embedded security, where my colleagues analyze this kind of attacks like a lot. And here you can actually see the calculation of an RSA algorithms. I'm not going into the detail, but they're doing some exponentiations and modular reductions. And to do it more efficient, you do reduce the complexity of a multiplication to a squaring if you can. And when you do this, then you think, okay, this is nice, makes it efficient and faster. It's actually a problem when you just take a look on the power consumption, because you can easily read out the private key. Yeah? And this is possible when the attacker just has the device, yeah, and can probe the device. A little bit more expensive attacks are fault injection attacks, where you shoot with maybe a focused iron beam on the circuit while the system is actually in operation, and then you create faults. And when you compare the results after a faulty operation, you compare it maybe with the correct operation, and then you can also again easily attack such implementations. If you have more interest in this topic, my colleague Falk Schellenberg, he's also somewhere here. Can't see him. He just finished his PhD, so we can call him Dr. Schellenberg, but he's not allowed to call himself Schellenberg, Dr. Schellenberg right now. So he's in exactly the stage during the PhD. Anyway, okay, and he's also an expert in doing hardware reverse engineering, where you use acid to open the chip and then analyze what's inside. Maybe you find weaknesses, maybe fuses or something you can use to read out keys, or maybe completely reverse engineer the system. Yeah. Another very interesting attack is the implementation of Trojans, specifically hardware Trojans, into the devices. And here's an example also of a colleague from Bochum, and he implemented a hardware Trojan into a high security USB drive, a high security USB stick. And this is also something we are targeting with the technology we are presenting. So with this knowledge and background in your backhead, when you are a designer of an embedded system, you have to handle it. So this means you have to create systems. Maybe you remember the talk yesterday about smart home hacking. There's a guy said, okay, the company is all the time complaining that it's military-grade security. Maybe they use some primitives like AES or something the military is using as well. But from the physical security point of view, there is actually no military-grade security in the market, not at all. They are very far away from the stuff the military is actually doing. So, however, also in this space, like the physical security, we have to go closer into the area of really physically secure the devices. And then I would say a classical developer for IoT devices will have a very hard time to put all this stuff in the design process, like developing side channel resistant algorithms, design a system where you can not probe data information between two chips. Let's say you have a security element on the device and also a classical microcontroller, and you don't want to manipulate it, then you have to somehow secure the entire system and not just a single chip. So this is a huge problem. So, and for all these applications, the big question is how to actually protect systems like this from physical attacks, coming from real IoT devices like smart home systems or alarm systems or something like this, up to financial systems like ATMs or maybe even satellites or other more critical applications, up to really high security applications. And maybe you remember the vintage verification talk from last year from the CCC, from our friends from Princeton University, actually from the Nuclear Future Labs. They have also some interesting use cases where this technology might be a nice fit. Okay.
Yeah. So at this point, you might be wondering, isn't there anything that exists already that protects our devices against tamper? And I will give an overview on what exists currently at the market. First of all, 4 different approaches to guaranteeing temper resilience exist, being temper resistance, in which temper is just made difficult for the attacker. Temper evidence, where any intrusion attempt must be evident. Going on, temper detection makes sure that a temper is detected and actively reported to the user or owner of a device. And lastly, the highest goal which we are trying to achieve with our solution is temper responsiveness, in which countermeasures are automatically engaged once a temper is detected. There's one big standard that at least covers how a temper responsiveness should work in practice, which is NIST FIPS 140-2. And in this standard, 4 increasing levels of anti-temper security are given. And we are trying to reach the highest level, which is level 4. And this is required for all highly sensitive environments that the US government has servers or appliances working in. So what does level 4 demand? First of all, any attack must be detected. Micro-intrusions, environmental attacks where like a deep freeze is conducted, and basically anything that somehow tampers with the physical integrity of the device. Secondly, breaches must zero all CSP. CSP standing for critical security parameters. So your cryptographic materials, your sensitive data, all of this must be deleted in the case of a tamper. Thirdly, the CSP must be separated from the main system, which is something you might already know from red and black systems on hardware protection modules. And lastly, the whole setup must be engulfed in a complete tamper detection and response envelope. We'll go into detail about that later. Sadly, no public benchmarks exist on which attacks are tried out to break around physical tamper resistance. So maybe there are some which are classified. We can't access them at the moment though. So coming to tamper resilience. This is something we will quite commonly see in everyday life, like the potting of electronic components, which is also sometimes done to protect against water damage. Or using totally secure one-way screws. I mean, there's no way we could get around this, right? Well, we can, obviously. We just need some proprietary tools or chip away at the electronic potting. So this is not really a solution. However, it just protects against vandalism in public places. It's very cheap and it's widely used, but not what we want for our system. Secondly, there's tamper evidence. This is something most of you will be familiar with as well if you try to repair your own phone, but you are not allowed to do it. On the upper right hand, you can see the typical warranty seals that are used in electronics. So you void your warranty once you remove it. The first real big issue that came up where tamper was the main concern was the Tylenol bottles. I don't know, does anybody of you know the story behind this? 2 or 3 hands. There was a serial killer in the United States who poisoned these small containers, and as a result, they started using these safety seals. But same as with the previous approach, widely used, cheap, and ineffective. There's a very nice talk on DEFCON 19, which we highly recommend, where they go into detail on how to easily circumvent these measures. One approach we want to point out, because it was mentioned last year, is shine bright like a glitter nail polish. You can very easily protect your laptop during shipping by just using glitter nail polish. First of all, you cover all screw holes of a laptop using stickers, just off the shelf, do what you want stickers, and then you cover the rim of the sticker with nail polish. Then you take a high-resolution picture of this nail polish and sign the picture with your private key and upload the photo. So the person receiving the laptop can make another photo and check whether the glitter particles are the same. Quite easy and very effective. However, this doesn't guarantee any higher level than tamper evidence. Coming to tamper detection. Now this is the first step where you really need to think about what you're doing, because having a tamper detection means you need some kind of sensor that is able to detect the opening or the tampering of the device. You can see on the top is a PCB that has a small photoelectric diode, and as soon as the case is opened and the light shines onto the diode, the system knows that it's been opened and probably tampered with. Several other methods exist as well, such as switches that just trigger when you open the case and so on. The benefit of this is that you don't need complex APIs. You can just have a small switch that can be read out, one-way switch, and you're done for. And false positives do not destroy the critical security parameters because there's just a notification going out. Maybe the notification might be wrong, but that doesn't destroy anything. Now, that's what we want to achieve: temper responsiveness. Current solutions are mostly based on meshes that are wrapped around the high security or hardware security module, because that is where temper is the biggest issue. And if you try to get into the bus lanes of these devices, you will destroy that mesh, and the capacitance, for example, of these meshes is different. This can be measured out by a deletion circuit, and that deletion circuit then automatically deletes any information on this device. This is state of the art. This is used by almost all hardware platform modules. But there's one big issue, or two big issues. First of all, you need a battery. If the battery runs out as a last dying breath, the system deletes itself, which is, of course, not wanted if you just want to store it on a shelf for some months. Secondly, you can only protect a very tiny area. Because it's quite hard to engulf a whole system in this mesh due to the need for air and heat spreading. So, FIPS 140-2 is really hard to obtain. There are only 3 worldwide modules that fulfill this requirement, and 14 modules have reached this requirement since, I think, 2005 or something. The constant need for power is, of course, troublesome, and no off-the-shelf solution currently exists. So you can't get any modules that say, hey, if you build this into your system, you are FIPS 140-4 level 4 certified. This, of course, makes retrofitting existing machines hard. There are several use cases where it's just desirable to retrofit an old machine. Especially ATMs are highly expensive. Having the vault in the bottom of this ATM where the cash is stored, moving it, reinstalling something, that's a process you don't want to go through if you want to just plug in a new module that guarantees temper. So now coming to where we are at, or what we want to achieve. Currently, both software and hardware solutions exist that try to verify temper, and our solution, which is symbolized by this little red dot, tries to go for a new approach that combines hard and software in a clever way while making it easy to redeploy existing devices after being fitted with our solution. Our solution is based on physical disorder, meaning we want to exploit small effects that are occurring during production. Some of you might know that electronic circuits have some small variations that are used to generate or to verify that the system has not been tampered with. And we go into a similar direction. Usually physical disorder is something you don't want. You want everything that you produce to be exactly the same, but you'll never be able to due to these microscopic effects that you can see up there. So we're using physically unclonable functions. I'm sure some of you will have heard of them. Could you give me a hand? Okay, that's the majority. Nice. So I'll keep it brief. You take a challenge that you throw into some kind of random system and you get a response out, and thus you can build a good old challenge response pair. We'll focus on just having a weak PUF, meaning we have only one challenge and one response, but we are sure that our entropy we have in our physical environment is sufficient. The properties are, they are very easy to evaluate, but very hard to predict. So you need to be able to conduct an evaluation very, very quickly, but be not able to simulate the environment using advanced simulation tools and extract the PUF response. Secondly, they're easy to manufacture, but hard to duplicate. So even if you put this thing into a CRT machine and really scan every layer and try to 3D print it or something like that, you won't be able to get the precision you need. Now to some mathematical aspects, there exists the notation of algorithmic tamper-proof. Most security goals or most security games that are played in cryptography are based on having mathematical functions that you want to reduce your problem on. And ATP extends this model by saying, okay, but what if we don't have a black box of crypto that we have an input and an output to, but what if we can tamper with all of the internals as well? And the researchers had 3 items they wanted to have checked, and then they say, okay, this is algorithmic tamper-proof. First one, there needs to exist some kind of secure hardware storage in which there cannot be, is no possible way to read when the system has been tampered with. Secondly, the device must be able to self-destroy itself. And thirdly, there must be some kind of hardware that cannot be manipulated with by an attacker. It may be read, but it must not be changed. And the first criteria has already been fulfilled by some colleagues from Heidelberg. They presented on CHES in Heidelberg in 2006. They used a small coating that they applied to an integrated circuit, and they were able to apply sensors to the integrated circuit that measure the capacity of the coating. So they had 30 of these sensors overall, all over the circuit board, and then they shot a small hole using gallium beam and created a 100 micrometer by 100 micrometer by 1.5 micrometer hole, and they were able to successfully detect this and have this chip be unusable. This is not the resolution we are going for, because most solutions we are aware of target the rough military requirement of 300 micrometer hole with a 300 micrometer diameter. This is what we are going to go for as well. So now we're coming to our key idea that Christian will present.
Okay, perfect. So I guess we learned already a lot. We learned the concerns, the problems. We learned the state-of-the-art solutions. We learned that really wrapping a system in a mesh which can actually detect 300 micrometer holes is kind of a goal we want to achieve. And this FIP standard 142 level 4 tells us that we have to do this as a complete envelope around the system. And right now this is only possible for kind of PCBs, but not for really entire systems. And the idea we are using here are coming actually from a completely different area, but touches like the concept of physical unclonable functions. So, and what we are using are actually electromagnetic waves, specifically the propagation effects of waves when they touches surfaces in between the transmitter and the receiver, and vice versa, actually. So these physical effects are very complicated. So there are complex effects, like classical, maybe well-known effects like reflection, diffraction, absorption, scattering, refraction, and also some nonlinear effects. Later I will show you maybe a little bit more about these details. But this is the idea. And actually the channel can now be characterized by something called channel impulse response. So here you have an example, someone is sending this function S from T, and E from T is a function the receiver will receive, and the channel is H from T, and this is characterized by exactly the change of the signal. And this is so the source, let's say the source of entropy, which extracts the entropy out, coming from this physical disorder we are using. Channel state information is pretty much, or contains pretty much the same information, just in a different way. It's actually represented in the frequency domain, and is in a specific semantic that it fits very well for equalizers and filters, specifically on the receiver side, but for modern systems also on the transmitter side. So we are using now this technology called wireless physical layer security and apply it in an enclosure. So this means we use the electromagnetic waves and send them from inside of an enclosure in the enclosure, in the environment, and estimate a fingerprint, so the generous pulse response at one or maybe several different antennas. Yeah? And here we have an example how such a fingerprint looks like, just for the magnitude. Yeah? There are also phase information, but we keep this out, maybe for simplicity. This enclosure can be, in this case, for example, an ECU, so a control module of a car, but it can actually be more or less everything. So we did this for ATMs and for a couple of other systems we are actually not allowed to talk about, but we can do this also for very more complex structures, even if there are moving parts and even if there are temperature change, then it will get more complicated. But we skip this just to give you an idea how it actually works. Yeah. And then a very important part of the algorithm is that we use this enclosure fingerprint to generate a cryptographically usable key, yeah, with a security level of, let's say, 128-bit, based on a statistic test and or entropy estimator. Yeah, so this is the general idea. Yeah? And if someone tries to tamper the system by maybe drilling a small hole in the case, he will automatically destroy the key. Yeah? And maybe a small spoiler, yeah, this is already the destruction, the self-destruction mechanism David was talking about. Huh? So this is the core idea. Yeah? And now the question is, okay, what kind of wavelengths we use? Yeah? So we use electromagnetic waves. You maybe know that depending on the wavelengths, you get kind of a bigger or higher resolution as higher the frequency is and as smaller the wavelength is. And then you can get actually more information out of the environment. The propagation effects are also a function of the wavelengths, and there are even more complicated parts. But this is, I guess, like the good basics you have to understand. Huh? So which of the frequencies are well suited for us? So there's, of course, a very wide frequency range from very low, like 3 kilohertz, up to terahertz technology, and even up to light frequency space. However, we are using actually frequencies in the area between 300 megahertz and 60 gigahertz. Yeah? So we have a wavelength of about 1 meter to, let's say, up to 1 centimeter. Yeah? So now the major question is, so why is this working? Yeah? We actually know there's kind of the rule of thumb that changes of electromagnetic wave propagations are somehow related to an object size with the size of the wavelengths. Yeah? And even if we use 30 gigahertz, we have a size of 1 centimeter, and then maybe only 1 centimeter change we can achieve. So what is the idea here? Why is this actually working? Huh? So it's working because we are manipulating the antennas in a way that we extend the near field of the antennas. And in this case, we can actually go from the wavelength dependency down to a thousandth of a wavelength dependency. And when we use, let's say, just ISM bands, yeah, which are the only ones we are actually allowed to use, yeah, due to the regulation, we go, we come, for example, for 433 megahertz from 70 centimeters down to 0.7 millimeter resolution. And when we use 5 gigahertz, we can even go down to 6 micrometer resolution. Yeah? And this is good. Yeah? So what can we do now? So we can actually now achieve an algorithmic tamper-proof. Yeah? Why? Because we generate a key, so the blue key here, from the inside. And this key can only be recovered from the inside and when the integrity of this enclosure has not been violated. Yeah? So if nobody changed something from this. And then we can actually achieve the goal of read-proof hardware, because the key is not stored digitally. Yeah? The key is the environment and the physics. If you change the physics, you destroy the key. And therefore, you also have the feature of self-destruction. And now you can use the key to encrypt stored data, which are integrity protected in the device. And in this nice combination, you achieve physical, an algorithmic tamper-proof. Huh? And the interesting features here are actually It's a little bit more complicated, but you don't have digital keys anymore stored in the device. Yeah? Of course, we have to make a difference. If the device is offline and goes in the online state, then it extracts a key of the environment. And when the system is online and does some kind of self verification, there's another different algorithm working. So we have to be a little bit more, have to apply a little bit more complex mechanisms here. But at the end of the day, we don't have to store digital keys. We have to take care, of course, that when in the online case the system gets attacked, that the key gets erased very fast from the RAM, and then we, of course, have to think about like freezing attacks and stuff like this. However, at the end, we can actually somehow achieve the goal. Due to the mechanism themselves, we also don't need a battery for deleting or erasing or zeroization circuit, yeah? Because the data, the cryptographic security parameters are all the time encrypted on the device. If the attacker opens the device, he can find encrypted data, encrypted with the key he already destroyed because he changed the physics of the environment, and that's it. Yeah? And we can show. Lars will show you a very nice demonstration we just prepared for the C3, yeah, where we can actually retrofit very standard hardware, in this case a single board computer, using very cheap enclosures. Huh? So maybe a high-level overview for a system. Yeah, maybe you have a host system, maybe the computer in an ATM, yeah, and you connect to the secure boot, or maybe even to the TPM of this host system, our FISAC testbed, which consists a radio with at least 2 antennas. Yeah? We learned, we estimate the channel between sender and receiver, and vice versa, and to extract a response, like the PUF response, and then an algorithm or a mechanism to extract the key out of this fingerprint. Yeah? And this is the thing we need to add to the system. Of course, sometimes we need to add also some kind of sealing or enclosing material around the system. This can be aluminum foil, but this can also be some kind of small meshes, like copper meshes, for example, which fulfill better air conditioning capabilities, stuff like this. And then still challenge is how to actually securely bring power and the data communication inside the system, passing the enclosure material.
Yeah. So like Christian said, now I'm going to show how we can build a low-cost proof of concept, and we bought a demonstrator here. So yeah, we're leaving the theoretical part mostly and going to something more practice. First of all, we're going to use physical disorder, like mentioned before, for generating some enclosure. And what we also need is radio-enabled commodity hardware with at least 2 transmitters, but there also can be more. And as mentioned before, we use aluminum foil we have here, and we use this cool box. It's a lunch box where you can put in noodles or something. So the first proof of concept demonstrator is using a Raspberry Pi. So it has connected 2 narrowband radios, which are sending in 868 megahertz with 2 megahertz bandwidth. And as an enclosure, we use a smaller one of these boxes and aluminum foil. But the problem is that the resolution is not so high, so we built another one. So the demonstrator we bought here. Therefore, we use an APU single board computer, which is serving our protection module. It's equipped with antennas, 4, so we have a 2x2 spatial system, MIMO system. So it brings us 40 megahertz bandwidth at 5.5 gigahertz, so there's more resolution. We just using for the enclosure this lunchbox. So, yep, switching the camera, please. Yeah, so this is our APU. Here are the antennas, 4 of them, and the cool stuff. So we put the APU inside the box, placing the antenna somewhere, and yeah, putting in some more enclosure randomness with this aluminum foil, putting it just over the system, and closing the box with this. So we switch to the demonstrator. Okay.
So we need to change the screens. Sorry. Kann ich nicht. Okay. Okay. Sorry.
Okay. So let's start with the demonstration. Yep. So first of all, we have we have 3 GUIs for different demonstrations. Okay, I don't get it. Why? Okay.
Come on.
Yeah. Okay.
Okay. This is of course very handy.
Ja. Das ist einfach so.
Okay.
Okay. Yeah, let's try this. So the first GUI is just showing a 3D modulation of what the 4 spatial channels actually are measuring. So that's how it looks like. Yeah, you can even really fancy move it. So you see, if we don't doing anything to the system, it's relative constant, and it's really typical looking. Yeah, for the whole time. So, but what if we open the device? When we open the device, we see there's happening very much, and if this we put this away, so many things happens. It doesn't look like before again. And if we put it back here, we still see it's not the same like before. So we destroyed the enclosure the way how it was before. So this is a very primitive attack. Well, we can of course think about an attacker which is more clever. We brought this Angry Birds with us. It's our little needles with a tiny Angry Bird on it. Yeah, camera switch maybe. Yeah, this one. It's very evil. Yeah. So this is camera switch again, please. This needle is, or this bird is very angry and wants to probe maybe some buses in our system and wants to go into our system. So we show what happens, or how it looks like when this happens. Yeah. Cool. So we have another demonstrator, which is showing yeah, some, or which is using some metrics, so we can not just monitor it with our, so the changes are persistent visible. So yeah. Yeah. Okay. So first of all, we are generating some reference values you're seeing now. This shown is the Euclidean distance. Maybe some of you know this metric. And now we are just comparing all measures which are coming from now on with the first measures. So we see there's a little variance we are measuring, but it's more or less very reliable. So, but what if this angry needle comes, okay, inside? There are huge changes in the system. So, and even if I pull this angry bird again off, the systems are persistent. It's very good visible. Yeah. Okay. So then we have a third GUI, which is also showing this in a good evaluation system. So how we can generate a key of this, because these were just some metrics where you can look at it visually. And now we're gonna generate a key. First of all, we're generating a reference value, then valid values, so you see the system works. And then we perform an attack again and measure again. So the clue idea is now that we can generate from the reference and the valid measurement the same key. Yeah, that didn't work. It's okay. Yeah. So we see when we measure in the beginning, we get different, or we get a bit error rate from a valid measurement by 22%. And an attack bit error rate by 47%. Then we are doing some information reconciliation where we used not the optimal parameters, so we corrected the bit error rate to at 9%. And after this, the strings are hashed into another value. So when the information reconciliation doesn't really work well, so we don't get a bit error rate by 0.0, of course we go to a bit error rate by nearly 0.5%. Yeah, 0.5. Well, we can optimize this more and more over time. So you see the curves above, where the white, I think, is the reference measurement we had. And the green one is the valid measurement, so they are very similar. And the red one is the measurement after the attack. So the characteristic really changes a lot. And with more parameter optimization, it is possible to generate a key perfectly. Yep. Ja. Okay. What?
We're innocent, I swear.
Okay, again. Geht das? Okay. So there are some pictures if the demonstrators wouldn't have worked, so I skipped them. And we go to the key extraction, how this works, and what are the design requirements for fingerprints. We have three design requirements for fingerprints. First of all, the key quality. The key quality is very important because when if we generate a fingerprint where every values are just zeros or ones, there isn't really a randomness. And if this isn't achieved, well, it's not so good because we want at least 120. It was going away. Yeah, 128 bits of randomness to be extracted. The second point, which is important, is the reliability. So if we measure and measure and measure over time, we don't want that the system generates different keys. So we always want to get the same key generated, because when we destroy our own key with a false positive, that's very bad. The last point, which is important, is sensitivity. So we want to detect even the smallest to detect even the smallest attacks. And if our system gives us a very good key the whole time, but doesn't detect any attacks, that's very bad. Yeah. So this is reliability versus temper sensitivity. Reliability means when we measure again and again, we get a very low bit error rate, and when an attack is happened, we just get a very high. So this wouldn't get corrected by information reconciliation. What we're actually doing is we have a reference measurement. We have valid measurements. They get quantized, and after this we do information reconciliation. The goal is, of course, that after this information reconciliation we have the same value in our valid measurement and our reference measurement, because after this step the values are hashed, and so even one wrong bit would lead to a bit error rate by 50% or nearly 50%. So I skipped this for because time, I think. So summary. We learned three things. First of all, that physical access enables major attack vectors. Therefore, bus probing, which the evil bird should demonstrate, and of course some things like side channel attacks, power measurement, and stuff. Next thing is that there are no system-level temper protection for commodity hardware existing at the moment on the market. So especially no things which are working without battery. And the last thing we did was presenting a solution we call Enclosure PUF that is based on standard hardware, so it's very, very cheap. And yeah. We can deploy this on many systems, so there aren't new systems to be created. We can extend IC security and PCB security, and it fulfills the ATP criteria. So thank you very much. Are there any questions?
If you do have a question, please line up on the microphones. If you have a question on the internet, just ask on the net. It's fine. I think we have one online question. Single.
There are two questions.
Okay.
There are two questions from the internet. The first one is, what kind of enclosures are stable enough over a long time and in changing environments for this approach?
Sorry, could you repeat that?
What kind of enclosures are stable enough over a long time and in changing environments for this approach?
Yeah, this is a very good question. Yeah, it's so the reliability is actually super dependent on the application. Yeah, so this really depends on the environment. If it's an aluminum case, it's a case of steel, made of steel. It's a combination. In which environment is it installed? Do we need to secure the system during transportation or just after it gets installed? So it's really application dependent. The answer is extremely application dependent. Yeah? There's no clear answer. Yeah.
Second question, how difficult is to distinguish between attack and just bumping on the case of the device?
Well, it's a good question. This is probably the easiest way to denial of service the system. You can just pump on it, yeah. And this is, it's again the same problem than for HSMs, yeah. You can drop an HSM and try to use it afterwards, yeah. in most cases not possible anymore. So this is again something where we have to parameterize this triangle. I mean, key quality is nothing we can really change. This is given by the physics and the measurement system, but sensitivity and reliability is something we have to agree on kind of a compromise. And this is also dependent on the application. Yeah.
Thanks. Microphone number 1, your question.
Hi, thanks for the talk. I have a question. Is it possible to have some kind of backdoor planted into this kind of system? Some kind? No, I mean like some kind of hole, so you can just plug some probe
we
in
thought
it?
about this for a moment, because if you have a false positive and you destroy your critical security parameters, of course this is terrible. And what we thought about was that we could we initialize the system in a secure environment. And it might be possible, you can code it, to have a function where you can extract the legitimate key right off the start and store it in a somewhere safe location. So yeah, you can back it up if that's the question, but having a typical backdoor that enables us, yeah, we can just apply some kind of temper that will go undetected. That's not something we ever built.
Yeah, sorry. The question is kind of like, can you have...
Excuse me, one question.
Yeah, not a backdoor itself, but maybe some kind of weak point. So later, someone else can do this kind of probe and extract your keys afterwards. So you just...
No, not that we plan to do so. No.
I mean, we are also very open to search for collaboration, specifically for partners to try to attack the system. I mean, as I said, my shy colleague Johannes, he's doing nothing else than trying to attack the system. And until now, we didn't found any potential useful attack. Yeah, but I mean, of course, we could add backdoors, but this is nothing we will do. Yeah.
All right. Microphone number 2, your question.
Hi, Christian. Nice work. Just a few questions. How do you calculate the secrecy capacity for the entropy? And what do you use for quantization, information reconciliation, and privacy application?
So all our secrets from the company are us. So mutual information is estimated by a k-nearest neighbor mutual information estimator, and then we subtract just the mutual information by a potential attack from the mutual information between, so X is the reference and Y is a legitimate case, while Z is the attack. Yeah, and this is how we calculate the capacity. And as I said, we use a k-nearest neighbor entropy estimator, which is also, so all your questions are answered in my dissertation. For quantization, we use an equal distributed quantization scheme, and for information reconciliation, we use a fuzzy extractor based on classical error correction codes, with a good parameterization, which doesn't work in the demo, but yeah. Good question. Thank you. Yeah.
Can you do the converse? Like, I've ordered 1,000 chips from a factory. Can I show that they're actually equal and not contain any hidden bug?
So this is a question where we really like people who are sponsoring our work by sending us 1,000 chips, and then we can figure this out.
What we did do, however, is we evaluated 100 different environments that were all equally constructed. We can talk about this in more detail later on, but we did evaluate 100 different environments that were only slightly different, and no two fingerprints were even similar.
Yeah. Okay. Signal Angel, any more questions from the net?
Two other questions from the internet. The first one, the method requires a precise clock for frequency stability. Is there any mitigation to compensate for high gravity applications?
I didn't really understand it. Sorry. Can you repeat it?
Yeah. The method requires a precise clock for frequency stability. Is there any mitigation to compensate for high quality applications?
Yeah. So. Yeah, I mean, this is one of the biggest problems we need to solve. We can talk about this topic offline, yeah? So if you want to know how to maybe correct face information or stuff like this, you can write an email. We have this email address 35c3@fisec.de, and then we can maybe talk about this offline.
Microphone number 2.
Hi, thanks for the great work. Actually, what you presented here was only detection of problems at boot, not in the runtime. So actually, I can boot the system, open it, and probe it for the key. So
Could you please state your question?
So what do you have any counterattacks?
Yes. Yeah, I mean, this is a good comment, and this is something I said at one slide, maybe you remember, that there are 2 protocols. One protocol when we are coming from the offline to the online case, and then one protocol which evaluates the environment during runtime, which is not part of this presentation. I think to answer this question properly, it makes also sense to talk about this maybe offline, if it's okay. Yeah.
Microphone number 1, your question?
So in your pin demo, what have you done to make sure that the tamper trigger is actually based on the presence of the hole or the pin or probe or so on, rather than deformation of the entire case?
We can't, actually. So when you do some torsion of the case, you will destroy the key. So depending on the application, we need maybe mechanically decoupled systems, where maybe influences from the outside are not changing the enclosure inside. So I would say a very...
I was asking the opposite. I mean, are you sure that you've actually measured the presence of a hole rather than deformation of the case in your tests?
So in this demo, I'm not sure, but in our lab environment, I'm pretty sure, because we fixed everything, and there was just a motor which is doing the whole, everything is fixed.
Great, thanks.
But yeah.
Signal Angel.
Question from the internet. How can I trust the system that during production the physical key was not extracted by the manufacturer, as it is not changeable by the owner of the system?
Yeah, this is a very good question. And it's not a question we can actually answer with this technology in general. I mean, we can think about solutions, trustworthiness by the manufacturers, but we could also think about something like the initialization of the system is not done in the manufacturing process, but afterwards, or maybe partly somehow. But this is, I would say, this is a general problem for manufacturing.
There's one solution we thought about, and that is that the system comes delivered in an uninitialized stage, and then you, as the end user, you did it. You put something in that wasn't in there before, and there are several things you could think about, like metal meshes that you, as a user, as a final user, just insert and pick yourself. So this is something the manufacturer cannot guess.
No.
Thanks. Microphone number 2.
How does this system compare to the one published by Fraunhofer Isaac last year, which, from my point of view, as I understood it, just measures the integrity of a foil that is wrapped around instead of the whole physical sizes? That seems more reliable to me. How does your system compare with that?
So maybe you saw the reference in our slides. So Vincent Imler and his group was in our reference. So as we said, the difference is the PCB level and the system level. So when you wrap a foil around an entire system, in this, I mean, the prototype system was like this big. You will have huge problems. I mean, when you think about an ATM to put a foil around it, it will be very complicated. So I think this is the biggest differences between like PCB or chip level security and system level security, what we do. Yeah, but it's still comparable. Yeah.
So you mean it's difficult to foil around a large system?
Yes, exactly. Okay. Yeah, and then heat problems and stuff like this. Yeah.
Okay, thanks.
Yeah.
Microphone number 2 again. I think you were first.
Yeah, thank you. For me, it seems like this is really, really even more than usual PUF temperature sensitive. How much have you looked into that?
With respect to temperature?
Yeah, I would think it would change a lot. So if you're wrapping a whole ATM that does get warm, someone bumps against it, it seems like you're going to have your data removed like every single day.
Yeah, so Johannes is like nothing because this is kind of his current task. So yeah, I mean, temperature stability must be given somehow. We can extract fingerprints for different temperatures. We have a resolution of about 1 degree. So when we change the temperature of 1 degree, we kind of have to reinitialize the system. We have to take care that this is given. We can do this in the initialization phase, but this is something important. And we did a lot of measurements with cooling chambers to do exactly this. Yeah.
And the reliability stays the same.
I mean, when you reinitialize the system for the different temperatures, you achieve the reliability. Yeah.
Okay, thank you. By the way, you're missing a site on page 21. Sorry.
Thank you very much. We were
All right. We're out of time for this talk. Are you guys still around for further questions?
Yeah.
Late in the building, I mean. Yeah. Okay, cool. If you, well, first of all, thank you.